Drodzy Państwo, ostatni panel przed przerwą będzie dotyczył skutecznego zarządzania intensywnymi opadami deszczu. Bo to szybkie ostrzeganie i skuteczne działania zaradcze to jest coś, co jest niezwykle istotne, jeśli chodzi o nie tylko infrastrukturę, o której słuchaliśmy przed chwilą, i bezpieczeństwo, ale przede wszystkim jeśli chodzi o ratowanie życia ludzkiego. To ratowanie życia ludzkiego jest najważniejszą, choć nie jedyną korzyścią, jak się okazuje, z wdrożenia systemu monitorowania powodzi, monitorowania intensywnych opadów deszczu, o którym opowie nasz kolejny gość, pan Tobias Menzel z OTT Hydromet. Zapraszam.
Okay, thank you very much and welcome to my presentation today about the effective heavy rainfall management. So I want to present key aspects of a state-of-the-art flood monitoring system, its benefits, its reasons for implementing such a system, its goals, and also speak about a few technical details. And at the end of my presentation, I will also give a short, well, let's say, glimpse into the future, because I want to, well, say a few words about AI prediction-based forecasting systems, which are applied by a few of our customers. Okay, let's continue. So this slide basically makes it very easy for me, because it basically just summarizes what has been mentioned impressively and extensively in some of the previous presentations. So there is a significant increase of heavy rainfall events across Europe, and these events pose a significant threat to municipalities, and we need to better prepare for those events. Heavy rainfall events usually happen happen suddenly on a very small scale, and that makes it very difficult to predict these events. And also, if you look, we have also seen that if you look at the forecast models, typically they have grids spanning over several kilometers, and these models are just not dense enough to capture all the fine details of stormwater events. And also, the existing monitoring networks usually lack the density required to provide meaningful data because the closest representative stations could be just too far away, so that you could rely on that data. And that leads, all in all, to the conclusion that if you really want to be better prepared and take protective measures before damage occurs, you need your own flood monitoring solution and also forecasting solutions. And this is, well, the idea of this presentation. So if you want to set up a flood monitoring system, what's the idea behind that? So what you want is to collect data in real time and also to monitor critical infrastructure, because this helps to identify a flood early enough to increase warning times and enables you to start taking your measures, as I said, before damage really occurs. And this kind of flood monitoring system should be capable of measuring, the key parameters of that indicate the intensity of a flood event. And this is mainly, obviously, water level, its precipitation. It can also be soil moisture. It also helps a lot if you have cameras for remote visual monitoring. We have just seen the presentation about critical infrastructure. And all the data that you collect, of course, should be made available digitally as well as mobile, and should also be fed into your models that you can create your forecasts and your warnings. So these are the basic elements. And of course, now it's a little bit like a technical background on the next slides. Of course, the most important and leading parameter is water level, because usually during flood situations, you respond to rising water levels. And we, as a monitoring company, offer here different solutions to measure water level. And one of them, the most commonly used ones, I want to present here shortly. And one of them is the contactless radar sensor, which is kind of a product that is newly available from my company. It is installed outside of the water, so it cannot be damaged by anything that happens during a flood situation. It's very accurate. It's a very small sensor. It can easily be mounted to bridges and provide reliable data. If you want to go into the water, of course, you can always work with classic pressure probes installed directly in the water, also very precise measurement of levels possible, very cost-efficient installations as well. So that is, as I said, the most commonly used level sensors. If you want to know about a critical situation before the water levels start to rise, of course, you also need to measure precipitation. And precipitation is always a challenge because it's highly distributed data, highly distributed information, especially during convective or torrential rainfalls, and therefore you need, a certain number of stations. And if you want to measure precipitation as accurately as possible, you should use a weighing principle due to its lack of moving parts. It also offers a low maintenance and gives you the most accurate data possible, and you can really call it like Met Service standard. So if you rely on weighing precipitation sensors, you can also use the data to calculate return periods of your precipitation event, for example. If you look more into that, you want to catch the spatial distribution of your rainfall, and you just want to extend your network in a very cost-efficient way, then you can also use radar-based precipitation sensors. They basically scan the sky around the sensor and can get from the radar wave reflections information about intensity and intensity of your precipitation event. They're not as accurate as the weighing principles, but still provide meaningful data, especially during stormwater events. And one step further, if you want to optimize your data, we also have seen pictures of weather radars. You can also use optical disdrometers. They do not measure only intensity, they also measure the type of precipitation, so you can distinguish between rain and hail and drizzle and snowfall, for example. And as they directly measure the drop size distribution, they're especially useful in combination with the big weather radars, because you can, from the drop size diameter, you can calculate a parameter, the so-called radar reflectivity, and this is used to improve the quality of the results of weather radar outputs. So you can better quantify your weather radar data that is available. Okay, so one of the questions I also frequently hear is, how many stations do I actually need? And well, the answer is as simple as it gets. The more stations, the better. And if you look into the literature, you find figures like stations being representative for an area of 3 to 5 square kilometers, or stations no more than 4 kilometers apart from each other. So that are, well, guidelines you can use. But of course, it always depends on your local orographic conditions and also, of course, on your local topography. But one thing is sure, and here just a number for the density of the official, let's call it like that, official precipitation network ran by IMGW. They have maybe 1,000 stations, maybe a few less, and that gives you a density of only 1 station for every 300 square kilometers, and this is by far not enough to provide meaningful data for local catchment areas. Okay, cameras, of course, always helpful. As you have seen in the previous presentation, you can monitor remotely critical infrastructure. You can identify blockages early enough. You can send people only then to the respective stations if really action is required. And it saves a lot of resources, especially during the emergency situations. You can also connect those cameras to data loggers. The data loggers can kind of activate, depending on certain thresholds, transmission of pictures to the data center, and that makes it also a very power-efficient solution in case you have limitations with your power supply. Another very interesting parameter that is more and more frequently used in this kind of flood monitoring system is the soil moisture. You see here on this picture a capacitive sensor that measures soil moisture not only at one position, but at several positions every 10 centimeters. So it gives you a profile. And, well, the soil moisture is important for your surface runoff creation, so how quick that happens. If you have very dry soils, or if you have already pre-saturated soils from previous rain events, that means basically that fresh rainfall cannot infiltrate anymore, is turned into surface runoff more quickly, and you'll find it in your rivers and creeks just much sooner than, well, if it could still infiltrate. So it's an important parameter, and many of the hydrological models in use, they can use the pre-moisture to calculate surface water runoff for you, and that basically improves the quality. Of course, you don't need only stations, you don't need only sensors, you also need stations, and here, well, let's say there's also many different possibilities available that we can offer. So depending on your requirements, depending on what you want to connect, how many sensors, what power supply you have, if it's an external power supply, if the station should run on their own batteries, there are different stations available, from combined all-in-one stations to highly customizable, well, control cabinets. And for the sake of this presentation, I want to mention, well, let's call it our new showpiece, which is a new fully integrated system that is called, well, flood monitoring system, and it integrates a radar sensor, a data logger, a communication unit, and also the power supply. It can be very easily installed. It has a very small form factor. The data logger itself is smaller than a Tetra Pak containing 1 liter of milk. You can run it on batteries only. You can use a small external solar panel, so everything is ready for simple, easy, and inconspicuous installation in your network. Now, this slide can get a little bit messy, so I apologize for that. So that's a real-life example of a small municipality in Luxembourg. It's less than 10,000 inhabitants, and they have been affected by heavy flooding in the past and decided to take actions. And the first actions they want to implement is basically, well, a flood monitoring system, and they decided to use in their network 3 precipitation sensors. In the center of the village, it's a weighing principle plus 2 radar systems. Here on the left side, you see that they also use the soil moisture as parameter in their network. They have 2 camera-only stations. They have 3 level-only stations. And now comes the messy part. They have 9 combined stations, camera plus level. So they really try to capture as much as possible information and data and send this data to our Hydro 3net hosted solution. There is a map view. You can watch the time series. You can create your own dashboards. You can embed the pictures that come from the station. And you can also display, if that data is available, weather radar data, like it is here provided by the German Weather Service. And also provided by the German Weather Service, there are special forecasts, 10-day forecasts for several meteorological parameters, also freely available. Here, for example, the airport of Poznan and the 10-day rain intensity forecast, where I took a screenshot a few days ago. So this is also information you can use in order to be better prepared for your events. Now, last but not least, as I have promised, a few words about AI-based prediction systems. And here I want to mention the example of the city of Goslar in Germany, who have implemented a kind of innovative project recently after they also have been affected by heavy flooding. And they use AI-based algorithms to enhance the accuracy and timeliness of their flood predictions. And to make it clear, you can see here already the network. Also, artificial intelligence needs data, needs measurement systems. So the first thing that city did was also to implement a flood monitoring system based on they monitor more or less our usual suspects, water level, soil moisture, also precipitation. and even flow velocity. And this data this data goes into the AI model that is based on something that is called long short-term memory networks, which is particularly good in analyzing time series data. It also analyzes historical data and tries to identify patterns. And the big benefit here is that it can also identify patterns of extreme events that are not included in the training data. So that could be a solution for the real extreme events to also better predict those. And based on the data and based on these identified patterns, predictions can be made for the next 2 to 4 hours. And they have proven to be very successful and reliable because the system is already in operation for a few years, and the customer is more or less very happy and came for himself to the conclusion that this is really a useful tool if you have the right infrastructure in place to enhance your accuracy of your forecast and to be better prepared for such events. Also, I forgot to mention one benefit is also that the system, the forecast accuracy improves over time because the more data it gets, it just learns from that information, and forecast accuracy will improve over time. Good, this is basically all I wanted to share with you. I hope it was not too quick. And that you could gain some new insights in the importance of such flood monitoring systems. We are happy to help together with our partner Retensia PL. We also have a few systems at display outside in the conference hall. So feel free to reach out, and then maybe we can start designing your solution. Thanks a lot for your attention.